Today, we're going to be divisibility detectives and see how each divisibility condition gives us one more clue at what the number will be. To start off, let's review the basics, the divisibility rules. For a number to be divisible by 2, last digit is even, so 0, 2, 4, 6, 8. For a number to be divisible by 3, sum of digits is divisible by 3. 4, last two digits divisible by 4. 5, last digit is 0 or 5. And 6, it's just divisible by 2 and 3, which you can check over here. 7, it's not that important, so you can look at here if you're interested. 8 is the last three digits divisible by 8. 9, sum of digits divisible by 9. 10, you all know, last digit 0. 11 is you look at the sum of the odd positions digits and the even position digits, and then you find their difference and see if that's divisible by 11. And remember, it's not the odd digits, but the odd number digits, so like the first digit, the third digit, the fifth digit. And for 12 and 15, you just look at each of their factors, so 3 and 4 and 3 and 5. And you can find another video on the channel where I cover these in much more detail, the basics. And the prime factorization, you just express a number in terms of its primes. I'm sure you all know about that. So let's see how the clues for divisibility. Let's see one problem that uses divisibility in action. Okay, let z be a 6-digit positive integer such as 247, whose first three digits are the same and as the last three digits taken in the same order. Which of the following numbers must also be a factor of z? Interesting. So basically, our numbers of the form ABC, ABC. Right? The first three digits are the same as the last three digits taken in the same order. ABC, ABC. But then how do we know which of these numbers it will be divisible by? The clue here is we can break this apart. Notice how this is just ABC is a 3-digit number, right? So it's the 3-digit number ABC times 1,000. What will that be? That will be ABC followed by 3 zeros, right? Plus simply the 3-digit number ABC. And that's just ABC. And notice how if we add them up, it gives us ABC, ABC, which is our original number. Aha, but now we can factor this. ABC times, this is times 1 over here and times 1,000 over here. So times 1,001. Aha, so we know our number is divisible by 1,001. But wait, none of these choices are 1,001. Now what do we do? Well, if you remember, it's always a good thing to memorize the prime factorization of 1,001. It's 7 times 11 times 13. And if you didn't know that, you could have just tried these choices and it wouldn't have been too hard either. But this is definitely a good thing to know. And using this in mind, we can see the answer is clearly 11. And none of the other choices will work. So 11 is our answer. The key idea here, encode the condition of the problem and then write it algebraically, and then after that we just express it as this times 1,001. We get 11 as our answer. Okay, let's try this problem here. What 4-digit number has tens digit 2 and units digit 8 and is a multiple of 16, and when its digits are reversed, it's also a multiple of 16. Cool. So this is a kind of an interesting condition, isn't it? It has tens digit 2, units digit 8, and it's a 4-digit number. It's divisible by 16, right? It's a multiple of 16. Okay? But we also have that when its digits are reversed, the result is a multiple of 16. So 8, 2, blank, blank. Now let's call these two blanks A and B. Then this will be B and A once we flip the number. So this is the original number, this is the flipped number. So when are both of these numbers going to be divisible by 16? Let's first take a closer look at this number over here. When will it be divisible by 16, right? We need both of them to be a multiple of 16. Both the original number and the new number. So we've got 82 followed by 2 random digits. So essentially we can rewrite this as 8200 plus the 2-digit number BA. And just to be clear here, it's BA the 2-digit number, not B times A. So first of all, what is the remainder 8200 leaves when divided by 16? Well, you can divide it out using long division, or you can see this clever trick, 8000 plus 200. Now, remember, for a number to be divisible by 16, last 4 digits have to be divisible by 16, which is, there's only 4 digits here. But you can notice how this is 8 times 1000. 8 is 2 cubed. 1000 is 2 cubed times 5 cubed. So this is divisible by 16 because it has more than 4 factors of 2, or has 6 factors of 2 in fact. So this leaves a remainder of 0 when divided by 16. This, on the other hand, we can just simply do long division if you'd like. We can get that it leaves a remainder of 8 when divided by 16. So the overall sum leaves a remainder of 8 when divided by 16. Okay, so this part leaves a remainder of 8 when divided by 16. That means that for the whole number to be divisible by 16, this part also must leave the remainder of 8 when divided by 16. So there's not going to be that many possibilities, so let's just write them all out. They can be 0, 8. That of course works. Okay. And it could also be 24 plus 16 plus 1640 plus 1656 plus 1672 and 88. And nothing else works beyond that. Too bigger than 100, so it's not 2 digits anymore. So these are our only possibilities for BA. And okay, so now for which one of these possibilities is this number also going to be a multiple of 16? Let's write that here. So these are the corresponding flipped digits A, B. Again, it's a 2-digit number, not A times B. So we've got 80, 42, 04, 65, 27, and 88. Okay, so when will this number be divisible by 16? Let's explore. Notice how this is just going to be AB, the 2-digit number, times 100 plus 28. And 28 leaves a remainder of 12 when divided by 16. And that means for the overall sum to be divisible by 16 or leave a remainder of 0 when divided by 16, this part must be leave a remainder of 4 when divided by 16. And okay, so we've got AB, this 2-digit number, times 100. So what is the remainder when 100 is divided by 16? Well, you can do that out if you'd like. 100 divided by 16 leaves a remainder of 4. So when AB times 4 plus 12, or AB times 4, this thing has to leave a remainder of 4 when divided by 16. And there's a shorthand for writing this, which we'll learn in the modular arithmetic video in a future video. But for now, remember that this product, when divided by 16, leaves the same remainder as simply taking each part remainder when it's divided by 16 and multiplying them together. So this must leave a remainder of 4 when divided by 16. And that means that AB itself, this part, must leave a remainder of 1 when divided by 4. So 1 when divided by 4 is what this number must leave a remainder of. 1 when divided by 4. Right? Because if we divide by 4, you can imagine writing this as, if it must leave a remainder of 4 when divided by 16, you can imagine writing it as 16a plus 4, so that when you divide by 4 to both sides, it becomes 4a plus 1. So therefore, and this is just the same thing as remainder of 1 when divided by 4, right? So AB must leave a remainder of 1 undivided by 4. Which one of these possibilities satisfies that? Not 80, not 42, not 4, not 27, that's 3, and not 88, it's 65. So AB is 65, so the 4-digit number is 6528. And that's our answer. So let's quickly recap. First thing, write it in this notation, AB28, A2BA. Cool? Okay, then we've got AB times 100 plus 28. And then we would write it as 8200 plus BA. Right? We're just breaking it apart into two pieces. So you find the remainder when this is divided by 16 and see what must happen for this to be divided. This is 8 when divided by 16, the remainder. So this must be 8 when divided by 16 as well. Look at the very few possibilities, find the corresponding value for AB, and then see that this is just AB times 100 plus 28, the 2-digit number AB, right? Want to be clear there. And this is the same thing as the 2-digit number AB times 4 plus 12 when divided by 16. And we can see that that implies 4 times the 2-digit number AB must leave a remainder of 4 when divided by 16, or that the 2-digit number AB must leave a remainder of 1 when divided by 4, and 65 is the only one that satisfies that property. So 6528 is our number. Original one. Cool. Now let's explore this AMC problem. A number is called flippy if its digits alternate between two distinct digits. For example, 2020 and 37373 are flippy, but 3883 and 123 are not. How many 5-digit flippy numbers are divisible by 15? This is a divisibility rule question. So notice that the pattern of the number must be something like this, because the digits alternate between two distinct digits, A and B, right? Divisible by 15. We know that. That means divisible by 5 and divisible by 3. What must happen for it to be divisible by 5? This digit over here must be 5 or 0, right? Can it be 0? No, because that means the first digit would be 0. And that is not a 5-digit number if the first digit is 0, right? So that means it has to be 5, so we already know the value of A. That wasn't too bad, wasn't it? 5B5B5, right? Now the real part of the problem is figuring out B. But we know the remainder when this is divided by 3 is, or it is 0 when divided by 3. It's divisible by 3. And divisibility rule for 3, we've got 5 plus B plus 5 plus B plus 5, 15 plus 2B. This thing must be divisible by 3, right? Sum of digits. And 15 is obviously divisible by 3, and that means 2B must be divisible by 3. Okay, so then, if 2B must be divisible by 3, 2 is clearly not divisible by 3, so that means B must be divisible by 3. And what are the only possibilities for B divisible by 3? 0, 3, 6, and 9. So the answer is just 4. A simple but cool problem that utilizes, you just look at the form AB, AB, A, 15, 5 and 3, right? And then 5B, 5B, 5. And then you simplified it to that and see, okay, now 2B must be divisible by 3, so B must be divisible by 3, our answer, 4. And you can check out these written examples. I explain them in great detail, so you get a lot of insight and intuition you can gain from these examples. And you can check them out in the free Mastering AMC8 book. You can find the link to that book in the description. It has many problems and many examples you can check out. Also, by the way, join the Discord, the Omega Learn Discord, to ask problems and discuss and ask for help on and different questions you might have. Okay, so now we're going to move on to this seemingly complicated looking theorem, but don't worry, it's actually pretty simple. Basically, the number of powers of p in n factorial. So let's say a question says, let's say you have something like 30 factorial. what if we find the prime factorization of 30 factorial, what's the power of 5 in 30 factorial? How would you do that? One way is to expand it out and do a lot of ugly calculations, but here's a cool little trick you can use. So the key thing here is you just do, let's say it's instead 33 factorial. So let's say we're asked to find the power of 5 in 33 factorial. Okay? So the key thing here is that this is a very simple trick you can use. So you do 33 divided by 5. That's 6 point something, right? 6.6 actually. But what we do is we ignore the decimal point. So we remove everything after the decimal point is just 6. And then we take that 6, do 6 divided by 5. That's 1.2, but we, again, ignore the decimal. So just 1. And then 1 divided by 5, if we remove the decimal, that's 0. And now what we do is we just add all these values up. So 7. It's that simple. Let's take another example just to be clear. Let's say powers of 7 in 25 factorial. You do the same thing. 25, or let's say 75 factorial. Okay? We're asked to find the powers of 7, so what would the exponent in the prime factorization of 7 be? So you just do 75 divided by 7. If you remove the decimal, that's 10. Now 10 divided by 7, removing the decimal, 1. And 1 divided by 7 is 0. We just add these up, we get 11. It's that simple. Now let's see this cool problem here, which uses the cool property we just learned. Find the number of zeros at the end of 100 factorial. Okay, how do we do this? Find the number of zeros. So when will a number end in a 0? Notice that for every 0 at the end of a number, let's say we have some giant number like this, it means it has to be a multiple of 10. So for example, this number will be a multiple of 1,000, and 1,000 is just 10 cubed, and 10 cubed is just 2 cubed times 5 cubed, right? So, as you can see here, for every 0, there must be, for each 0, there has to be a multiple of 10. There has to be one factor of 10. And for each factor of 10, we need a factor of 2 and a factor of 5. So all we essentially have to do here is to find the number of zeros at the end of 100 factorial, we just have to find the number of powers of 2 in the prime factorization and the number of powers of 5 in the prime factorization. And we can use our simple trick. And just to be clear here, this trick only works for primes. So you cannot just directly do 10. You cannot just directly do this trick for numbers like 10. You have to do it separately for each prime, if that makes sense. Okay, so 100 factorial. 100, let's do 5 first. Divided by 5 is 20. 20 divided by 5 is 4. 4 divided by 5, removing the decimal, is 0. And that's it. So there's 24 factors of 5, right? Now, how many factors of 2? That's 100 divided by 2, 50. 50 divided by 2, 25. 25 divided by 2, 12. 12 divided by 2, 6. 6 divided by 2, 3. 3 divided by 2, 1. And then 1 divided by 2 is just 0, so we're done. We just add all these up. 50 plus 25, 75. 75 plus 12, 87. 87 plus 6, 93. 93 plus 4, 97. So there's 97 factors of 2 and 24 factors of 5. So what's our answer then? So our prime factorization will look something like a bunch of random terms times 2 to the 97 times 5 to the 24. How many zeros will there be? The answer, 24. Why? Because for a 0, we need both a factor of 2 and 5, not just a factor of 2. So if we kind of combine this, we can also rewrite it as 2 to the 73 times 10 to the 24. So there's 24 zeros, and we then run out of factors of 5. So only 24 zeros at the end. So 24 is our answer. And you can find all these practice problems in the free book I mentioned earlier. And now we're going to explore factors. There's some really cool tricks to find number of factors of a number. And if we're going to take that out, in the next video, you can click on it right there. See you next time.